Good afternoon, and welcome to the USDA Human Nutrition Research Center on Aging's weekly seminar series. My name is Paul Jakes. I'm a senior scientist here at the HNRCA and the host of today's seminar. Before introducing today's speaker, I have just one minor housekeeping announcement. And as always, we welcome your questions for our speaker, but I would like to remind you to ask your questions using the Q&A icon on the webinar toolbar, not the chat box. And I encourage you to add your questions as they arise during the presentation. Today, I take great pleasure in introducing our speaker, Dr. Kelly Cara. Dr. Cara is a postdoctoral fellow in the Population Science Department at the American Cancer Society, and that's through a joint appointment with the Winship Cancer Institute at Emory University. Her primary research interest is how following a healthy diet over time impacts a person's health. Her research in prospective cohort studies makes use of repeated dietary intake measures to examine cumulative effects of following healthy diet patterns over time on various health outcomes. Her current research at the American Cancer Society focuses on how plant-based diet patterns contribute to lower cancer incidence, mortality, and cancer severity. Prior to heading to the American Cancer Society, Dr. Cara was a doctoral student here at the Friedman School of Nutrition Science and Policy at Tufts University. And I had the opportunity to serve as a member of her doctoral dissertation committee. Her thesis research involved a complex and fascinating project focusing on the role of healthy dietary patterns on cognitive ability, cognitive reserve, and cognitive decline, the results of which she will present today. And with that, I will turn over the microphone to Dr. Cara.
Thank you, Paul, for the introduction, and thank you all for the invitation to present. As Paul shared, I will be discussing my research from my Tufts PhD thesis today, which examined the effect of dietary patterns over the life course on global cognitive ability, cognitive reserve, and Alzheimer's disease in the 1946 British Birth Cohort. So I have no financial conflicts to disclose, and my funding is listed here. But I do think that it's important to make a personal disclosure that I follow a whole food plant-based dietary pattern, and this does shape my research interests, which focus on contributing new research to improve our understanding of the role that healthy plant-based dietary patterns can play in achieving and maintaining health and preventing chronic diseases. So my research really aims to inform dietary guidelines by examining both the potential benefits and challenges of these dietary patterns. For today's talk, I will provide some background, and then I'll give an overview of the 1946 British Birth Cohort data, which is a truly unique data set. I'll also go over my methods and results, some strengths and limitations, and future directions. And we should have about 10 minutes for your questions at the end. Alzheimer's disease is the most common cause of dementia, which is a group of symptoms affecting memory, reasoning, or other thinking skills. And it primarily affects individuals aged 65 and older. Now, while some cognitive decline does naturally occur as we age, the rate and severity of decline that's associated with Alzheimer's dementia is not an actual part of healthy aging. Alzheimer's progression follows a continuum wherein healthy cognitive functioning can gradually transition to pre-symptomatic changes in the brain, which can lead to mild cognitive impairment and eventually dementia in some, but not all, individuals. In this final stage, the symptoms also follow a continuum as they worsen from mild to severe over time, and ultimately Alzheimer's can lead to death, and it typically occurs within 4 to 8 years after diagnosis. Although I have recently heard about a woman that was diagnosed and lived with Alzheimer's for up to 20 years. Alzheimer's is responsible for the death of 1 out of every 3 seniors and is listed among the top 10 leading causes of death in the United States. It's currently ranked at number 7 with a significant decrease in incidence from 2021 to 2022. And it's worth noting that this is a change from the significant increase that was documented from 2019 to 2020. Despite the poor prognosis for those diagnosed with Alzheimer's, some people with this disease show no clinical symptoms, despite the presence of brain disease pathology. That is to say that given the same degree of brain degradation, some individuals show no abnormal change in their cognitive ability and daily function, while others experience the rapid and severe cognitive and functional decline that's typically associated with Alzheimer's. So this unexplained individual variation in cognitive function, despite equal brain disease pathology, is attributed to cognitive reserve, or our peak premorbid cognitive ability. With Alzheimer's affecting millions of people in the US and globally, there is clearly a need to slow or halt the rise in cases. But there is no known cure that can stop or reverse the drastic physiological changes that can occur in the brain, and few treatments are available to change disease progression. Despite this, it is possible that Alzheimer's may be prevented, its progression could be slowed, and disease onset could be delayed. Therefore, evidence for the role of cognitive reserve and potentially modifiable lifestyle risk factors like diet is urgently needed, but currently scarce. Existing evidence suggests that healthy dietary patterns, and especially those that are rich in plant-based foods, which are high in antioxidants and mono and polyunsaturated fats, may be able to improve cognitive and brain outcomes by reducing oxidative stress, improving vascularity or blood flow to the brain, and by contributing to the development of neuroplasticity and strong connections in the brain. Yet the influence of dietary patterns on cognitive reserve and Alzheimer's related cognitive decline is not yet known. So that is what we set out to investigate. The overall objective of this body of work was to examine how dietary patterns over a life course relate with global cognitive ability, cognitive reserve, and the clinical expression of Alzheimer's disease and related dementias. So the study aims were to investigate the association between dietary patterns and global cognitive ability across the life course, to compare the degree of influence of long-term alignment with different dietary patterns on cognitive reserve, and to investigate whether cognitive reserve modifies the association between Alzheimer's pathology and cognitive decline, as it is theorized to do. So this research involved secondary analyses of an ongoing closed prospective cohort that had both dietary and cognitive data collections from childhood into older adulthood. So here I'm going to share an overview of the data source and general methods, but I'll get into some of the study-specific methods when I discuss the results. The National Survey of Health and Development from the Medical Research Council Unit for Lifelong Health and Aging at the University College London was developed as a follow-up to a 1946 maternity survey in Great Britain. The resulting 1946 British Birth Cohort included a random selection of 5,362 infants who were born to married mothers during the same week in March of 1946. These infants were sampled from British birth registries and represented all regions of Great Britain and different family backgrounds, different socioeconomic backgrounds. 52% of the cohort members were males, and data have been collected 25 times from this cohort over 75 years, while data collection is actually still ongoing. At the age of 68, 49% of the original cohort still contributed data, and just 7% of the original cohort has been completely lost to follow-up. The Medical Research Council Unit manages and funds the study and provides access to the data for bona fide research projects at no cost. And my research utilized de-identified data and was deemed exempt from IRB review by our Tufts Social Behavioral and Education Research IRB. For our studies, the primary exposure was dietary patterns, and dietary data were collected at 5 time points in this cohort from age 4 to 64. We had access to the raw dietary data, which included both foods and their nutrients that were derived from UK food tables. To identify broad dietary components like whole grains or seafood in the participants' diets, we manually linked the food data with the USDA food pattern equivalents and ingredients databases, which contain commonly consumed foods in the US. And since the UK food system differs from ours, we linked foods based on closest matching descriptions. Together with the UK nutrient data, we then created healthy eating index scores and scores for 3 plant-based dietary indexes. We used the 2015 and 2020 Healthy Eating Index, or HEI, as a measure of diet quality throughout our research. And the 2020 version was released partway through our analyses, but components and scoring standards are the same as the HEI 2015, as shown here. Most of you, I think, are familiar with the HEI, but for those of you that aren't, dietary intakes of each component are scored proportionately based on minimum and maximum intake standards per 1,000 calories consumed. And the total HEI score is the sum of the 9 adequacy components, which are foods to eat more of for good health, and the 4 moderation components, which are foods to limit for good health. I will discuss the components and scoring for the plant-based diet indexes later. Our primary outcome was different forms of cognition, and cognitive measures were collected at 8 time points in the cohort, from age 8 to 70. At each age, different tests were given to measure different cognitive abilities. So we pooled these to create global cognitive ability percentile rank scores at each age. The National Adult Reading Test was given at age 53, and we used this as an indicator of cognitive reserve in the studies, as is commonly done. At age 69 to 71, some participants additionally contributed neurological data in a neuroscience sub-study called Insight 46, and I'll describe that in further detail later on. In addition to the dietary and cognitive measures, data collected across the cohort's lifetime comprise numerous demographic and health and lifestyle factors, including measures known to influence cognitive development and cognitive reserve, such as those listed here on the slide. So, to investigate the association between dietary patterns and global cognitive ability across the life course, our first study addressed these 2 questions. What is the relationship between dietary patterns and global cognitive ability over time? And is there potentially a life stage when diet may matter most for cognition? And I'll pause here to add a note that this work has been submitted for publication, but is not yet published. The analytical sample included participants with complete data at birth, 2 or more years of dietary data, and 2 or more years of cognitive data, where for both the diet and the cognitive measures, we required that participants would need at least 1 measure in childhood and 1 in adulthood, so we could identify trends across the life course. The analytical sample represents 57% of the original cohort. To address our research questions, we first needed to map out trends in dietary patterns and cognitive ability over time. So for this, we used group-based trajectory modeling, which requires at least 2 data points and assigns individuals to groups with trajectories that are most similar to their own. Models can have any number and shape of trajectories, and there are statistical and theoretical approaches that help guide these decisions. So we based our models on US data that are presented in the Dietary Guidelines for Americans, which show a U-shaped pattern for diet quality across life stages based on healthy eating index scores. So using the 2015 or 2020 healthy eating index scores, we hypothesized that we would see in the cohort a normal pattern group that would follow a similar U-shaped trajectory. And then we modeled 3 trajectory groups altogether, expecting that there would be some people that would have typically higher and some that would have typically lower diet quality than normal. And the results are depicted here and generally support the hypothesized trajectories, where about 50% of participants were in the normal pattern group, this red line in the middle, 31% were in the consistently higher group, the green line at the top, and the remaining 19% were in the consistently lower diet quality group, the blue line at the bottom. Based on prior data, we expected an increase in diet quality throughout adulthood, but these trends did depict a stronger increase than expected. And unfortunately, there were no dietary measures between age 4 and 36, but we can see that dietary patterns in early life may have set the stage on average for dietary patterns in later life. So there was very little variability in H4 diet scores, which was in 1950. This was in England while they were still experiencing food rationing due to World War II. And this consistency actually creates a really unique opportunity to identify factors in life that may influence changes in diet as the cohort members aged. Still, these trajectories indicate that cohort members whose diet quality was higher at this early age of 4 tended to track with higher diet quality patterns over the life course on average, while those whose diet quality was lower at age 4 tended to track with lower quality dietary patterns over time. This may suggest that even subtle differences in dietary patterns in early life may influence our dietary choices later in life. And this supports the 2020 to 2025 dietary guidelines statement that it is important to establish healthy dietary patterns early in life. The same group-based modeling approach was used to test a 4-trajectory group model for general cognitive ability, where we hypothesized trajectories based on ideal and typical cognitive trends that were theorized by Cabeza and co-authors in 2018. So the figure on the left shows the ideal progression of cognition, where a higher peak in neural resources, this blue curved line, allows a person to meet cognitive demands, the pink line, even after their neural resources have declined into old age. The figure on the right shows a typical progression where cognitive ability does grow over time, but the peak neural resources are not enough. They're not high enough to sustain the individual once that decline starts to set in. So here, the eventual level of decline in neural resources surpasses cognitive demands. Based on this, we hypothesized that some cohort members would show stronger degradation of cognitive abilities relative to peers, while others would show some improvement over time. We also hypothesized again that some would have consistently higher and some would have consistently lower cognitive abilities than their peers. So to model cognitive ability relative to peers, we used each cohort member's average percentile rank for multiple cognitive measures taken at each age. Again, the hypothesized trends were generally supported in that some people showed a more rapid decrease in ability over time, this green line kind of in the middle. Others showed some improved ability over time, the red line in the middle, while some people consistently remained at higher cognitive levels, the yellow line, and others consistently remained at lower cognitive levels than their peers over time, and that is the blue line. Based on the percentages that are presented in the graph, you can see that there was a pretty even distribution of cohort members across these trajectory groups, but with slightly more participants in the consistently high group and slightly fewer participants in the improvement group. You can also see that there was a high degree of variability in cognitive scores in childhood, but less variability in adulthood, and especially at ages 43 and 70. We believe this happened because the nature of the cognitive tests themselves, where childhood tests were those typical of school-based assessments for topics like math, language, and reading abilities, while adulthood tests assessed cognitive functions like speed processing, reaction time, and memory. And note that there's also a big gap in general cognitive ability data between age 15 and 43. Now, one of the interesting things about group-based trajectory modeling is that models can be combined to see how different outcomes relate to each other over time. We combined our diet and cognition models in such a dual trajectory analysis to identify conditional probability of membership for one factor based on membership in the other. So in other words, for participants in the highest cognitive trajectory, for instance, what is the chance that they will be in each of the dietary pattern trajectories? So in the bar graph on the left, you can see that cohort members with the lowest healthy eating index score trajectory, which is the dark blue, they made up the largest proportion of members in the lowest cognitive ability group, the bar on the far left. Conversely, only a small portion or proportion of cohort members with the highest diet quality scores, that green bar, was in that lowest cognitive group. So the opposite trend was true for the highest cognitive trajectory, the bar on the far right, where very few participants showed low quality dietary patterns. We were also able to dig a little deeper to identify whether diet was a significant predictor of cognitive ability groups and whether diet at a certain age or stage in life was more predictive of group membership. For this, we used multinomial logit models comparing membership in the highest cognitive trajectory group, the yellow line, to each of the other groups, depending on HEI scores at each age. So across crude and minimally adjusted models, there was an inverse relationship between diet scores and the probability of being in the lowest cognitive group. And the association was strongest for ages 36 and 43 dietary patterns, where those with better diet quality were less likely to be in the lowest cognitive trajectory, that blue line, compared to the yellow line. In the fully adjusted model, which controlled for baseline covariates and diet at every other time point, age 43 diet alone remained a significant predictor, where for every 1 point increase in HEI scores at age 43, the probability of being in the lowest cognitive group declined by 4%. These effects were diminished for the middle cognitive groups compared to the highest group. So really, it's the extremes that were showing differences. Another interesting way to look at these relationships over time is to view radar plots at each age, showing what aspects of diet changed over time for each cognitive group. So here I've presented the 13 components that make up an HEI total score, and points closer to the outer circles indicate closer alignment with dietary guidelines for each component. So for the moderation items, sodium to added sugar, higher scores or dots closer to the outer line mean lower intake. So zooming in, we can see that age 4 diet was similar for the cohort members who were still facing that World War II rationing, but there are some subtle differences where cohort members that were in the highest cognitive trajectory group, the darkest blue line in this graph, showed higher intakes of total fruit and whole fruits, and possibly some higher total dairy and fewer whole grains at this age compared to those in the lowest cognitive trajectory. But the differences are pretty minor. By age 36, we can see stronger differences in dietary patterns starting to emerge, such that those in the higher cognitive trajectory groups had higher intakes of total fruit, whole grains, and total dairy, with lower intakes of refined grains and sodium. Changes over time also showed increased intakes of greens and beans and total protein foods by age 63. So what was the relationship between dietary patterns and global cognitive ability? Results from this cohort showed a positive association between dietary patterns and cognition over time, where higher diet quality trends were associated with higher global cognitive ability trends. And is there a stage in life when diet may matter most for cognition? Well, based on this cohort, we saw that age 43 and 36 dietary patterns most strongly predicted being in the lower versus the highest cognitive trajectories. And this suggests that dietary patterns in midlife or before age 50 may help sustain higher global cognitive ability over time. So moving on to the second study, we wanted to compare the degree of influence of long-term alignment with different dietary patterns on cognitive reserve in cohort members. So to do this, we addressed these two questions. First, how does one's typical dietary pattern relate to cognitive reserve? And how does long-term alignment with different dietary patterns influence cognitive reserve? So this work has also been submitted to a journal and is currently under peer review. Research suggests that certain aspects of our cognitive abilities are impacted in early stage Alzheimer's while others are not. So specifically, our acquired knowledge and experiences, which are considered our crystallized abilities, do not seem to be affected. This includes our general knowledge, our lexical knowledge or vocabulary, and our language skills, abilities like reading and writing. Because our crystallized abilities are less vulnerable to Alzheimer's, these are thought to be the best indicator of premorbid cognitive ability and therefore can be used to measure or indicate cognitive reserve. So among the various measures of crystallized ability that were available in the 1946 British Birth Cohort, The National Adult Reading Test, or NART, is the most commonly used as a measure of cognitive reserve. This was given to the cohort members at age 53, and we use this to represent cognitive reserve in this study. Here we wanted to compare different dietary patterns, so we again used HEI scores, but we also generated scores for 3 plant-based indexes, or PDIs, that were developed about a decade ago out of Frank Hu's group at Harvard. The overall PDI measures intake of all plant-based foods. The healthful PDI measures intake of healthy plant food groups, and the unhealthful PDI measures intake of less healthy plant food groups. The various food groups are shown here, along with animal food groups, which are reverse scored for all 3 of these indexes. So this means that higher intakes of any animal food groups result in lower scores for these 3 plant-based dietary indexes. Scoring for the plant-based components vary, as shown in the bottom table, such that higher intakes of any plant food groups result in the higher PDI scores or overall scores. Higher intakes of only the healthy plant food groups result in higher HPDI scores, and higher intakes of the less healthy plant food groups result in higher UPDI scores. Therefore, we hypothesized that positive associations with cognitive reserve would be identified for overall PDI and the HPDI scores, and that there would be a negative association for UPDI scores with cognitive reserve. For the analytical sample, participants needed a National Adult Reading Test, or NART, score at age 53. They needed 2 or more years of dietary data up to age 53, and complete data on all of our covariates, which I'll explain in further detail on the next slide. For this study, we were able to retain 47% of the original cohort. For our analyses, we used a series of multiple linear regression models that we repeated for each dietary index score. So to identify the cumulative effect of dietary patterns over the life course, we generated a mean diet score for any cohort members with at least 2 years of dietary data up to age 53. And I've got a box in the top right corner that indicates that nearly half of the analytical sample did contribute data at all 4 available data collection periods up to that age. Age 53 was the year that cohort members took that National Adult Reading Test, indicating cognitive reserve, our outcome for these models. So building on the crude association between cumulative diet and cognitive reserve, we next added sociodemographic factors, lifestyle factors, leisure time activities and health measures, and we repeated these 5 models for each dietary index. Results from the HEI fully adjusted model are presented here as a forest plot. And to orient you to this graph, I'll share that on the x-axis, we're showing adjusted mean differences in NART scores, where scores from 0 to 50 were possible. The rows show results for each quintile of HEI scores, where quintile 1 represents the lowest scores and dietary patterns that were least aligned with our US dietary guidelines. Compared to quintile 1, quintiles 3, 4, and 5 of the HEI scores showed significantly higher cognitive reserve and a clear stepwise association across quintiles. This indicates a dose-response relationship. In other words, at each interval of higher diet quality, participants showed increasingly higher cognitive reserve. We found similar results, but no clear dose-response relationship for the overall plant-based dietary index, where participants with the highest intake of plant food groups overall, regardless of quality, showed significantly higher NART scores compared to quintile 1. For those consuming the highest levels of healthy plant food groups, this included foods like whole grains, fruits and vegetables, and beans, cognitive reserve was significantly higher than the lowest quintile, and again, we start to see some semblance of dose response. Finally, those with the top 2 highest intakes of the less healthy plant food groups, which includes foods like sugar-sweetened beverages, sweets and desserts, fruit juice, and white potatoes, showed significantly lower cognitive reserve scores than quintile 1, and dose-response relationships were indicated here. So in a sixth model for each dietary index, we added childhood cognitive ability as a covariate. All covariates combined accounted for just over half of the total variability in cognitive reserve. And this graph shows the contributions by the different dietary patterns, where HEI 2020 scores helped explain the most variability in cognitive reserve. So just focusing on this HEI model, here we can see the unique contributions to variance explained for each covariate group, which were calculated by decomposing R-squared values using the Owen value. 48% of variance was unexplained by the models, and 22% of variable in cognitive reserve at age 53 was attributed to childhood cognitive ability, which is not unexpected. Typical diet based on HEI scores accounted for 3% of the variability in cognitive reserve, and other lifestyle factors like smoking, alcohol, and exercise accounted for another 3%. Therefore, when diet was combined with lifestyle, this 6% of variance accounted for a similar contribution to cognitive reserve that we would see by achieving one's first college degree. It's worth noting here that in previous research on cognitive reserve, diet typically has not been considered among other lifestyle factors. So these results provide some support for adding dietary patterns to other lifestyle factors that are typically examined when looking at cognitive reserve outcomes. Again, comparing dietary component scores across the HEI 2020 quintiles, we can see that participants with the highest scores were consuming higher levels of all adequacy components. Recall that these are average intakes from 2 or more dietary reports up to age 53 in the cohort, so I'm not showing these at each age. Especially notable here are higher intakes of greens and beans, total fruit, whole grains, and total protein foods. These individuals in the highest quintile were also consuming lower quantities of all the moderation foods. And notable here are lower intakes of refined grains and saturated fats. Similarly, this graph shows differences across the quintiles for the average healthful or HPDI plant-based dietary index component scores. Here, the foods in green represent those healthful plant food groups that should be increased in the diet. The foods in yellow are the less healthy plant food groups to be consumed in moderation, and the foods in red are the animal food groups which are to be limited in the diet based on these indexes. So similarly to the HEI, participants with the higher scores on this index, quintile 5, were consuming more of the healthy plant foods, especially including whole grains, fruits, and vegetables, plus they showed higher intakes of nuts, vegetable oils, and tea and coffee. Those in quintile 5 also showed lower consumption of the less healthy food groups with the exception of fruit juice, which was similar across groups, and less of the animal foods, except for dairy and fish or seafood, which were also similar. Based on these results, we were able to show how one's typical dietary pattern relates to cognitive reserve, and this cohort showed a positive association between cumulative mean dietary pattern scores and cognitive reserve at age 53. Higher diet quality throughout life was also associated with higher cognitive reserve. We were also able to address how long-term alignment with dietary patterns, different dietary patterns, can influence cognitive reserve. And in this cohort, those with higher levels of cognitive reserve showed closer alignment to dietary guidelines, higher intakes of plant foods overall, higher intakes of healthy plant foods, and lower intakes of less healthy plant foods. In our third study, we investigated whether cognitive reserve modifies the association between brain pathology measures that are associated with Alzheimer's and cognitive decline in the Insight 46 sub-study. So this research addressed the question, does cognitive reserve modify the clinical expression of Alzheimer's dementia? With this study, we tested the operational definition of cognitive reserve that was provided in a 2022 framework outlining 3 necessary components. First, we need measures of life course related brain changes, insults, or disease, or risk factors that theoretically would impact cognitive outcomes. Here, that's going to be our brain pathology measure. And next, we need measures of associated change in cognition, which is our measure of cognitive decline. And third, we need a variable that influences the relationship between 1 and 2. That is going to be our cognitive reserve measure. Our primary goal here was to demonstrate that cognitive reserve moderates the relationship between brain pathology and cognitive decline. And in other words, we're saying that cognitive reserve can protect against cognitive decline, even in the presence of brain pathologies associated with Alzheimer's disease. If effect modification could not be demonstrated, we at least wanted to demonstrate that cognitive reserve is associated with cognitive decline while adjusting for brain pathologies. In other words, while holding brain pathology constant, did cognitive reserve protect against cognitive decline? In the Insight 46 neurological substudy, brain pathology measures were available for 502 of the 1946 British Birth Cohort members. Brain imaging was performed using PET and MRI scanning, where PET scans provided data on the presence of brain amyloid, which is associated with Alzheimer's disease. And we had access to amyloid status as positive or negative, as well as levels of amyloid based on partial volume corrections, or PVC. MRI scans provided brain volume data where atrophy or brain shrinkage is indicative of Alzheimer's. We used total brain, left hippocampus, and white matter volumes relative to total intracranial volume to identify potential atrophy. We also used white matter hyperintensity data, which is a measure of lesions in the brain that are consistent with Alzheimer's disease and related dementias. Clinical expression of Alzheimer's refers to the signs and symptoms that show up in daily life with this disease. Here, cognitive processes used to solve new problems are most affected. These are referred to as fluid abilities and include the speed at which we process information, our executive functions like working memory that allow us to keep track of information, and the ability to reason our way through new problems. Because these aspects of cognition are most vulnerable to Alzheimer's, clinicians use tests of fluid abilities to determine cognitive decline that is greater than what we would expect in healthy individuals, and that may therefore indicate the presence of Alzheimer's. From the fluid ability measures that were available in this study, tests of working memory and of processing speed were repeated 4 times from age 43 to 68 or 70. So we calculated change in fluid ability using these 2 measures, the word list recall and the timed letter search, where cognitive decline was indicated by the difference scores from age 68 to 70 and the maximum score prior to that. To perform our analyses, we followed 3 steps that are prescribed in that 2022 Reserve and Resilience Framework outlining the operational definition of cognitive reserve. So first, we used a simple regression model to establish the relationship between cognitive decline and brain pathology. If such a relationship was established, we moved on to step 2, which added an interaction term to the model to demonstrate whether cognitive reserve moderated the relationship between brain pathology and cognitive decline. If step 2 failed, we moved on to step 3, which removed the interaction term and assessed whether cognitive reserve was associated with cognitive decline while adjusting for brain pathology. For each of these models, likely confounders were controlled for, and this series of steps was repeated for each of 5 brain pathology measures and the 2 measures of decline in fluid cognitive ability, that is working memory and processing speed. And the NARC scores at age 53 were again used to indicate cognitive reserve. The analytical sample for these analyses included participants with at least 2 fluid ability measures, one from age 43 to 63 and one at age 68 to 70. Participants also had to have at least 1 usable brain scan measure and a NART score at age 53. And this included 89% of the InSight 46 subcohort. Starting with cognitive decline measured by working memory, 2 brain pathologies showed significant relationships with changes in word list recall scores, amyloid status and white matter hyperintensity volume. So starting with amyloid, this graph shows percent change in word list recall on the y-axis, where negative numbers indicate decreased working memory. So here you can see that compared to participants with negative amyloid status, the box on the left, meaning they showed minimal or no brain pathology, those who were amyloid positive, the box on the right, had significantly greater cognitive decline while controlling for E4 allele status and epilepsy medication use. For white matter hyperintensities, participants with higher volumes of hyperintensities showed more severe decline in word list recall scores than those with lower volumes of hyperintensities. No relationships were established for the other brain volume measures and change in working memory. So we only moved forward with step 2 of our analysis process for these 2 measures, the amyloid status and white matter hyperintensity volumes. In step 2, we examined whether the cognitive reserve measure, NART scores, modified the relationship between change in working memory and brain pathology. For participants with amyloid positivity, those with low NART scores, this red box, showed significantly more cognitive decline than those with high NART scores, the blue box. The difference here showed about a 10% greater decline in working memory for people with lower NART scores, indicating lower cognitive reserve. However, for participants who were negative for amyloid, cognitive decline was similar, regardless of their NART scores. So these results indicate that higher cognitive reserve can protect against decline in working memory, despite the presence of amyloid, which is a brain pathology measure indicative of Alzheimer's. For global white matter hyperintensity volumes, this graph presents predicted mean changes in word list recall scores and the 95% confidence intervals from a model that was adjusted for total intracranial volume. And you can see that participants with the higher NART scores, the blue line, did show less cognitive decline than those with the lower NART scores across increasingly higher volumes of hyperintensity. But this interaction was not significant. These results suggest that high levels of cognitive reserve may be able to reduce decline in working memory due to greater white matter hyperintensity volumes, but this is not conclusive. So due to these inconclusive results, we moved on to step 3 for only this brain pathology measure. Now, as a reminder, in step 3, we're aiming to demonstrate that cognitive reserve is associated with cognitive decline while simply controlling for the presence of brain pathology, absence that interaction. This graph shows the estimated mean change in word list recall scores and 95% confidence intervals by NART levels, while additionally controlling for total intracranial volume and maximum word list recall score. So here we see that participants with the higher NART scores on the right showed significantly less cognitive decline than those with low NART scores on the left. And these results indicate that high cognitive reserve does protect against decline in working memory while adjusting for white matter hyperintensity. So I'll speed through this one just to say I repeated those steps again for decline in processing speed ability measured by that visual search speed test. And we didn't find any clear trends with amyloid levels. So it may be the case that processing speed and amyloid are in fact unrelated, or that change in processing speed by age 68 to 70, which was the endpoint of data in this subcohort for phase 1 of data collection, their change in cognition may not have been severe enough to detect a true relationship. We also found no effect modification here and no association demonstrating cognitive reserve as protective. So in conclusion, does cognitive reserve modify the clinical expression of Alzheimer's dementia? Well, in the Insight 46 sub-study, cognitive reserve protected against decline in working memory, despite the presence of brain pathologies in the form of amyloid status and white matter hyperintensity volumes. However, cognitive reserve showed no association with processing speed in the presence of brain pathologies. And it may be that cognitive and brain changes by age 69 were too minimal to detect effects. In summary, this examination of how dietary patterns throughout life influence or are related to cognitive outcomes results from the 1946 British Birth Cohort indicated that dietary trends that closely aligned with dietary guidelines were associated with better global cognitive ability trends over time. Also, healthy dietary patterns were associated with higher cognitive reserve or peak premorbid cognitive ability, and cognitive reserve protected against decline in working memory that is associated with Alzheimer's disease pathologies, but these results were not conclusive for processing speed abilities. The major strength of these studies is the use of that 1946 British Birth Cohort data, which has repeated measures for diet and cognition across 7 decades and beginning in childhood. Among all the longitudinal cohorts that I reviewed, this data set has the earliest available dietary data, while also providing data on multiple cognitive domains and brain imaging through the Insight 46 sub-study. The availability of these data in a single cohort enabled us to utilize a life course approach, which involved both longitudinal analyses and cross-sectional analyses that made use of the repeated dietary exposures data. However, these data also came with limitations. The dietary lifestyle and certain health outcomes data were self-reported, which can lead to reporting errors. And because the UK and US food systems differ, linking the UK dietary data with the USDA databases also has limitations. We tried to minimize these assumptions by using as much of the UK data as possible when creating dietary index scores. There were also limitations regarding the inconsistency of measures as the National Survey of Health and Development changed focus and changed hands over time. So this included some major gaps in data collection periods, some inconsistency across the dietary and cognitive assessment tools that were used, and the long duration of the study inevitably led to a high amount of dropout or attrition, rather, over the decades, resulting in a large amount of missing data. Furthermore, there is limited generalizability for the results of these studies. Due to the attrition that I just mentioned, there were differences in baseline cognitive scores for those included in study 1 and those that were excluded due to missing data. It's also important to point out that there are no race or ethnicity variables available in this cohort of individuals from Great Britain. That said, the diverse geographic and socioeconomic backgrounds of the original cohort and the balance between males and females does help to make the results somewhat more generalizable. Future research should build on this study of the 1946 British Birth Cohort by incorporating different longitudinal methods like latent growth modeling to further elucidate interrelationships between changes in dietary patterns and cognition over time. Examining phase 2 and phase 3 data from the Insight 46 neuroscience sub-study would include additional brain pathology measures, which we didn't have access to. This includes tau, which is an indicator of Alzheimer's disease. And furthermore, as the sub-cohort ages, we can expect further decline in cognitive abilities and greater levels of brain pathologies. This should enable investigators to better identify any potential effect modification by cognitive reserve. Future studies can also examine other proxies of cognitive reserve, like highest educational attainment and career complexity, whereas we used that National Adult Reading Test. And with the rich dietary data available in this cohort, other dietary patterns could be examined in relation to cognitive outcomes. Finally, these results need to be replicated in other populations, including those with different racial, ethnic, and cultural profiles, where dietary patterns and genetic influences on cognition may vary. That said, there are not a lot of cohorts that provide such detailed dietary and cognitive data, especially over the life course. So in my postdoctoral research at the American Cancer Society, I'm examining data from the Cancer Prevention Study 2, which started in 1982 and included nearly 1.2 million participants. Here we have verified mortality data from linkages with the National Death Registry up to 2020 for nearly 38 total years of follow-up. And in this time, 27,000 have died from Alzheimer's disease. Although this baseline cohort included only general dietary data, 24,000 participants have self-identified as eating a vegetarian diet. But from a brief 28-item FFQ, we identified only 4,500 who really reported no meat or fish intake. There were about 10,000 who reported consuming chicken or fish only, and 85,000 who reported consuming meat or fish 3 days per week or less. So we are currently looking at the association between these dietary patterns and all-cause mortality and cause-specific mortality from major chronic diseases that are listed among the top 10 leading causes of death in the US, and that will include Alzheimer's. Next, we'll examine diet quality in the CPS2 nutrition subcohort, which has repeated dietary data from Block and Willett FFQs. So stay tuned on all of that work. With that, I'd like to just acknowledge the extraordinary individuals who participated in the National Survey of Health and Development. These people have contributed countless hours in their personal data so that we can benefit. The MRC staff at the University College London have organized and managed this study for over 7 decades and were a wonderful resource as I went through this research. Of course, my co-authors and thesis advisors, Mei Chung, Paul Jakes, and Tammy Scott. I'd like to thank 2 statistical advisors at Tufts, Sarah Johnson and Misha Eliashu, and finally, my funding sources. And with that, I look forward to answering your questions.
Thank you, Kelly, for making a very nice presentation of some very complex analyses. So we do have questions in the queue. First question is from Nagla Alabadi, and she says, thank you, Kelly, for presenting this interesting work. Around slide 26 on the 3 trajectory groups of dietary pattern adherence to recommendations, around what proportion were exceptions? Example, low diet quality when young, but higher in older adult and vice versa.
Okay, can you read it for me one more time, please?
Yeah, it's basically looking at it around slide 26 on 3 trajectory groups of dietary pattern adherence to recommendations. Around what proportion were the exceptions? That is, those with low diet quality when young, but higher diet quality in older adult and vice versa.
Okay, so that I don't have that level of detail here, and I'll pull up the slide again real quick just to share it so people can see what we're looking at. No, it's not going to let me do it. I'll just say this: I don't have that level of data for that slide, and I'm trying to orient myself to it right now. I do want to pull it up. Sorry for the delay, just to make this a little easier. There we go. Are you able to see that, Paul, or no?
Yes. Yes.
Yeah, okay. So I believe this is the slide. I don't know if she can chime in or he can chime in. This is not looking at difference in age here. So again, if I understand the question correctly, the trajectories themselves were defined based on the data points at each age. But when we start to look at associations between these 2 trajectories, what we're really looking at is the probability of being in one outcomes group based on another outcomes group. So age is kind of taken out of this equation. So essentially saying that if my diet tends to follow a higher or lower trajectory over time, not at any one single time point, but my overall trajectory is higher diet quality, then I will tend to be in the higher cognitive group over time. Does that address the question, do you think, Paul?
Yeah, I mean, I think maybe it's just the proportion of people who are actually, because you have the trajectories where you're starting off higher and declining, and the other way you're starting off low and
Right.
increasing. Just those, what were the proportions for those two trajectories?
For the trajectories themselves,
Yeah, I mean, that might be the question, like itself.
yeah, I guess I'm not sure that I fully understand the question there.
Okay.
I can, yeah, sorry.
Oh, well, yeah, just go back because well, I think you have it right here because there's 22% of the people were in the trajectory where it started low and increased and 27% were in the, forgive me,
Oh, okay. Yes, yes, yes. Over on the right side, the graphs, those are the trajectory percentiles, the number of people from the cohort that were in each of those groups. That's just for, and the bottom one being the dietary scores. Most individuals were in that middle group, 50%. Yeah.
Okay. All right. The next two questions are from Larissa Constantino, but I'll ask them individually. So the first question, is HEI in 4-year-olds different in modern children?
In modern children compared to this group, I would say yes. It's interesting to compare the data from this trajectory. If you look at that bottom graph on the right, compared to that U-shaped graph that I shared on a previous slide with the US dietary data that was updated from 2020. That was the 2020 to 2025 dietary data. So I would say in terms of actual scores, if you look on that y-axis on that bottom right graph, it's about a 45% average, getting close to a 50% average, or a score of 50 out of 100 on the HEI. I believe that in the US, our scores are similar currently, but I could go back to that slide as well and we could actually look at it. But it's, let's see if I can get there. But anyway, the answer is it's similar, but not identical by any means. And I can get to it here. Just so that we have that, sorry to take the time to do this here. So 61 is what we showed in 2020 for the average for ages 2 to 4, and that decreases to 55 by ages 5 to 8 in the US population. If you recall that I mentioned the wartime effect on this 1946 British birth cohort probably is the most instrumental reason that their scores were lower. So again, averaging around 45, maybe getting close to 50. There was just no access, not much access anyway to meat. I think much less dairy. The breakfast was typically porridge. I don't know how good of a quality that would have been for the 1946 British birth cohort. So they were certainly a unique age group. And I would say that probably pretty consistently globally, we would have seen lower diet quality during that era. Good question, interesting.
Larissa's second question is, there is a connection between obesity and cognitive function. Have you tried to include in your models measures of adiposity?
I don't have measures of adiposity. The best I had was body mass index, and I believe that we did control for body mass index among our lifestyle measures on all of our models. Now, the trajectory models are not controlling for covariates, so that is not controlled for here or examined in association here.
The next question comes from Sarah Booth. And she says, thank you for a wonderful talk. When you consider your component scores, even the higher quintiles have relatively poor diets. Is it possible that you do not have the range of diet quality scores to really capture the contribution of diet to cognitive reserve?
Yeah, so for that's the second study for cognitive reserve. Yes, you know, there is variability in this cohort. It's a fairly large cohort, but to your point, we don't have scores that are ranging from the very, very low to the very, very high limits of these indexes. So yes, I do think that that's a possibility, that if we were to try this in a larger cohort with more variable data, we might see some differences. But again, that said, it's challenging to find really good quality detailed dietary data with good quality cognitive measures with such a long follow-up period. So there may be other limitations in those cohorts.
Okay. We've reached 1 o'clock, but I'm going to continue. We've still a number of questions in the queue. So next question is from Daniel Promislow, and he says, fascinating work, and asks, could you please comment on the role that socioeconomic background has on diet choice, and could there be effects of diet not measured by the current metrics, but which are captured by the socioeconomic class?
Yeah, absolutely. So the interesting thing about the 1946 British Birth Cohort is that the original aim was to identify how variation in social class might impact health outcomes for infants. After some of those relationships were established, they continued to look at later life outcomes such as cognitive outcomes, which is why we see some of those large gaps in data collection. Socioeconomic background certainly had an effect on diet. I think it absolutely has an effect on these cognitive outcomes. So we did control for that in all of our models. We have a rough indication, however, of socioeconomic background, and it's based on the father's employment at the time of age 4 to age 8 for these children. So it's, I don't have great financial or income data in this cohort. There's a lot of missingness in that variable. But based on the father's employment, we were at least able to control for social class. So, but yes, that certainly, I'm sure, plays a role in both of these, the exposure and the outcome.
Next question comes from Michael Grusak, and he thanks you for a very clear presentation and says, I'm still struggling with what cognitive reserve really means. He's not the only one.
Sure.
Means or represents. You mentioned neural resources earlier in your talk. Can you expand on these? You seem to base all of this on NART scores.
Right. I have based, I'm just going to look at this image real quick. I have based cognitive reserve on NART scores. That is not uncommon in clinical settings. NART scores can be used to help identify cognitive reserve, which is basically a sense of what is your peak cognitive ability before we start to see cognitive decline. Now, of course, it depends on the age that you are taking these assessments, because you can take an assessment at age 50 and still see some, cognitive peak beyond that point. But typically, we see pretty stable. You could use other proxies for this, would be IQ. So you see pretty stable levels once you reach a certain age. And so the idea with NART is that you are given words that are commonly understood, but difficult to read if you don't recognize the word itself. So meaning that the pronunciation is not obvious from the spelling. So you would need to have familiarity with the word, like naive, perhaps, to be able to recognize it on this assessment. So that type of skill set is fairly consistent once you get to a certain level of cognitive ability. So that's what this assessment is measuring. Cognitive reserve can be indicated by other measures like IQ, like I mentioned. I hope that helps, but really it's the idea that this is our peak cognitive ability. Things that influence it certainly are education and career complexity or work complexity. So it's not only education, but yeah, it's pretty stable once we see people reach a certain level.
Okay. The next question comes from Avani Mittal, and she asks, "Thank you, Kelly, for a great talk. I am unfamiliar with literature on Alzheimer's disease, and I'm curious if we know anything about its association with maternal diet during pregnancy. You mentioned this cohort was originally from a maternity survey. Is there any known association from this or other surveys, survey data excluding cases of malnutrition?"
Yeah, I haven't done that work, so I'm not going to be well suited to answer that. And I will say we were hoping to have even earlier life dietary measures to at least see if, maybe breastfeeding status or duration of breastfeeding may have an impact on Alzheimer's as a later life outcome, but we didn't have good enough quality data to address that in this study. I'm not familiar with that research though, so sorry. Maybe it'd be a good area for you to follow up though. We can talk.
One last question from Shelley Fong. And the question is, hi, really nice presentation. Have you tried to look into the association between cognitive function decline and dietary sodium intake in AD patients? There is some new sodium MRI studies showing the brain sodium content may be a new biomarker for AD.
Oh, that's interesting. No, I'm not familiar with that. I don't know if you all have heard people using this, and I don't know how much people are doing it, but some people have referred to Alzheimer's as like type 3 diabetes. So there have been studies that are looking at associations with other nutrients. Specifically, my work has only focused on dietary patterns, though. However, I will say from this data set really truly does have rich dietary data, and you could look at sodium or any other nutrient, micro or macronutrient that you were interested in based on this data. And these cognitive outcomes, especially in that Insight 46 sub-study, although it's a small group, they have some clinical measures that I think it'd be valuable to look at those types of associations, as you mentioned. So thanks for the questions. Great.
And thank you, Kelly. That's all the questions. So again, thank you for a very nice, very clear, very nice presentation of some very complex findings.
Yeah, great. Thank you.